I knew it wasn't on. You lied to me. This is not a good way to start, audience. Yeah, you could hear me before. Too loud now, or okay? Pretty good? Good, okay. So Clojure. So particularly I want to focus on the differences. I want to focus on things that are in Clojure that are not in Ruby, and that to maybe bring you some new ideas. And also a couple things that we can steal a little bit from Clojure and bring to our Ruby code. And by the way, I love questions. Questions are my favorite part of giving talks. Please don't feel like you need to wait to the end. Just raise your hand, get my attention. You're not interrupting. I love talking to the audience, especially after mate. Okay, so I just want to show you, this is not a tutorial, but I do want to show you just enough syntax to get us going. So this is a vector. In Clojure they call it a vector. It looks like an array in Ruby. It has those square braces around it. Notice there are no commas. Commas in Clojure are white space. You can include them if you like, if it makes it easier to read, but you don't need to have them. This is a list. It's another sequential data structure. It has slightly different performance characteristics than vectors, but it's just a collection of items in order. Here's a map. It looks a lot like a Ruby hash. We have these keys and values. This is the key name goes to the string Ben, and the key age goes to the integer 31. Curly braces. Pretty familiar. Here is where things start to look pretty wildly different. Function calling. How's this font in the back? Is this better if I revert? Worse? Big enough, or want me to go bigger? Great. So this is function calling. So to call a function in Clojure, you surround the function call and its arguments in parens. So this is the plus function with 2 arguments, 3 and 1. And if I evaluate this, we get 4. And you see that 4 right at the bottom here? Right there. I'm going to be evaluating things, and they show up right there. Is that big enough to see in the back? Great, okay. So when I say I'm evaluating this, you'll see the results show up right there. So 3 plus 1 comes out to 4. Here's another function call. str is a function that takes strings and jams them together. So if I evaluate this, we get hey there. 2 arguments to that function. And here's a slightly more complicated nested set of function calls. So the order of evaluation is we evaluate all the arguments to a function before we actually call the function. So first we're going to evaluate plus 1, 1, which gives us 2. Then we'll evaluate the second plus 1, 1, gives us 2. Multiply them together, and so this will give us 4. A little weird. It's called prefix notation. But it's actually pretty great, and you get used to it real fast. So that's actually enough syntax to get going, which to me is kind of amazing. Also, I've taught you all the precedence rules for Clojure. That's all of them. Arguments get evaluated first, then they go into their function. Kind of cool. So let's look at something a little more complicated. Function definition. Here's how you define a named function. This is the welcome function. So we create a list. The first element is the keyword defin, followed by the function name, followed by a vector of its arguments, and then the body of the function. So if we evaluate welcome John, we get hey there John. If we change this to Ben, hey there Ben. That's a function call and function definition. And like I said, we're pretty much ready to go. So now let's get to the really interesting stuff. I want to talk to you about immutable data structures. This is the most important idea in Clojure, to my mind. So in Clojure, data structures and data do not change. And I'll show you what I mean by that. So this def call right here binds this user var to this map. So if I evaluate this, I get back a response that says, okay, I bound something called user. And if we look at that, identity of user just returns whatever that thing is. It returns its argument. So we can see that we have age 31 named Ben. That's the map representing me. Now let's call this function assoc. So assoc takes a map, which is user, and a key and a value. And it sticks that new key value in the map. So if we call this, we see the map has been updated with my city. But if I go here and I evaluate what user is, it's still its original value. User has not changed. Assoc returned a new map. It did not change the existing map. Here's dissoc, which gets rid of a key from a map. So if I call that, you can see it's just down to age. But again, user is not affected. So this is kind of weird, right? We've all been programming, almost all of us have probably programmed in languages that have mutable data by default. Why would a language choose to do this? Well, it turns out there are a number of really great benefits that you get. So first of all is shareability. How many people have here ever had a bug where they passed an object into a method that somewhere down the road passed it to something that mutated that object without you knowing? Has anybody had that bug before? This can be, yeah, a lot of people. This can be one of the most difficult bugs to track down. It's really confusing. You can easily spend a day on this. It's very hard to understand. You know who's had a lot of bugs like this? Rails. Let's go take a look at what that. So what does Rails do? What do you have to do if you want to be sure you can modify something? What do you do? What's that? Duplication. Yeah, well, you copy it, exactly. So you call it .dup or .clone because you need to be worried. Like, okay, you've given me something. I do want to change this, but I don't know if I'm going to mess you up if I change this. So let me make a brand new copy of this, and then I can mess around with that and eventually return it back to you. So Rails calls .dup or .clone a handful of times. Let's see how many. This is the Rails code base. I'm going to use a search for .dup or .clone and count them. 384. And that is the 384 that they happen to know about, where they've remembered to do it. There's probably 384 more that they have not remembered that are bugs, just waiting to bite somebody. Immutable data prevents this entire class of bugs. And it does it almost for free. The performance characteristics of these immutable data structures are actually very good. They've been written very cleverly so that they're not slow, and they share structure between them as you change them. And so we can eliminate a huge class of bugs for free, which lets us share data. We're happy to share data between methods. We're happy to share it across threads. It's easier to cache. There's a whole bunch of these reasons, but I actually don't need to provide many of them for you because you actually already know this. You actually already know that immutable data is really great. And here is how I'll prove it to you. Let's imagine that in Ruby, I define a method on the integer class. I open up the integer class, or the number class, and define a new method called increment. Like I want to give like the equivalent of plus plus in Ruby. And so imagine if you called for.increment, and rather than returning you 5, a new value, I took what 4 pointed to and changed it. So that if you did 4.increment on the next line, you did 4 plus 4, it was 10. That would be insane, right? You would call me insane, and you would have these incredibly subtle, hard-to-understand bugs. But that's roughly what we're doing when we allow our data to mutate. So Clojure says things are not going to mutate. Maps are immutable, strings are immutable, sets, vectors, numbers, function names. These things are all immutable. They don't change out from underneath you. Now, another reason that we actually know this is Git. In this room, I'm sure we have like probably tens of thousands, on the order of tens of thousands of Git commits. How many people have had a really nasty, corrupted Git repository? A couple people. Okay, a couple people. Git is amazingly consistent. The fact that you can't change a commit and that it has a SHA pointing back through the whole history is really wonderful for consistency. I've basically never lost data from Git that I've actually already committed. I've lost stuff before I committed it, but that's my fault. And another way we know this is a good idea is think about goto. So the kind of program we do today is called structured programming. And structured programming means that we don't use goto to jump around. We used to write code that was like, okay, if x is more than 5, go to line 250. And then over here, if you know y is more than 20, go to line 640. And the reason we stopped using goto was because it made it really hard to answer a question. And that question was, how did I get here? How did I get here in my code? I'm doing these invisible jumps between things, and suddenly I'm here, and I don't know why. And there's not a stack trace that shows me how I got here. But we stopped doing that because it was really hard to answer that question. It was hard to reason about our programs. When you use mutable data structures, it makes it really hard to answer, how did my data get this way? How many people have had a thing where they're looking at an object because something blew up, they got an exception, they go, how is it that this thing is nil? Like, everyone has had this problem, right? Everyone has had this problem. It's hard to know how your data got to be in a certain state when anything can change it. When you can share it across to a method, and you need to know every method that that method calls to make sure that nothing gets mutated. So this is actually an idea that we can bring into Ruby. So I've been writing a lot of Ruby recently, a lot of Clojure as well, but I have basically stopped writing code that mutates things in Ruby as much as possible. Instead, I use these things called value objects. So a value object takes data in its constructor, and then all it will do from then on is like read that data or answer questions about that data, but it'll never change that data. And if I want to change the value object, I'll just return a new value object with new data in it. And I found that this has really, really improved my Ruby. So this is an idea we can steal. The data structures are not as nice. The performance characteristics are not there in Ruby. but we can bring this idea of immutability into some of the work we do today. Another way you can bring this in is at your database level. So think about if you have a user that can sign up for things, that can have a subscription. In the past, I would have said, oh, if the user cancels the subscription, delete that subscription record. And we basically have lost that data. We're treating our subscription as mutable. So now what I'll do instead is I'll record an end date and mark it as stopped, for example. And then if the user signs up again, we give them a new subscription record. And we treat all that data there as there's a fact that a user has a subscription, and I'm not going to blow away that fact just because something has changed. I'm not going to go back into the database and erase one of the fields and write new data. I'm just going to record new data. And I found this has made my programs much better. Questions so far? Everyone's fine with this? You're going to write all immutable data? Was that a question? Just stretching. An example of immutable data in Ruby? Sure. The question was, can I have an example of immutable data in Ruby? Yeah, symbols. Symbols are immutable, right? You can't mutate a symbol out from underneath you. And you know why we have that, right? It's so that we don't, if we use string keys in a hash instead of symbols, you can lose access to an element, right? Like if I had the string Ben points to my data, and then something else got a reference to that same string and mutated it to say John, now I can't look myself up by Ben anymore. So we use symbols in Ruby. We're like, that's a great idea. In Java, strings are immutable. But for some reason in Ruby, we decided, oh, well, we shouldn't have immutable strings. And now there's this work to like freeze strings. There's like that frozen string work. And it's all complicated. And I don't even know if it actually made it into Ruby because it's hard to add immutability in after the fact. So what I find myself doing is adding at the higher level with what's called a value object. So it's an object that takes data and then won't ever let you mutate it. It stays the same. Good question. Thank you. So to me, the natural question that follows from this is, if our data is immutable, how do we manage change? How do we actually show things that change? Because in the real world, things change, right? The number of people at your company goes from 50 to 51, and you need to be able to reflect that. So Clojure says, okay, data should be values, meaning a thing that is true at a point in time. And that should always be true, because you've said it is. Okay, you have 50 people at your company. That's a fact. That fact does not change because now you have 51 people. There's just a new fact. There were 50 people here. There are 51 people here. And so what should happen is there's some way, it would be nice to have a thing that says, okay, there are 50 people, and then points at the new fact that okay, now there's 51 people. And that's exactly what Clojure does, and it calls those things reference types. So let's look at a reference type. So here are the attributes that represent ThoughtBot as a company. The name is ThoughtBot, and we have an employee count of 50. And now, I want to create a reference type to hold that map. So you can think of a reference type as a box, and the box holds immutable data. So the box has the name ThoughtBot on it, and we put in the attributes of ThoughtBot. And if I want to change how many people work at ThoughtBot, I have a very controlled process for taking that old value out and putting a new value in. But both those values are immutable. So the values don't change. The box just holds a different immutable value. And the way we switch something in and out of the box is very controlled. And this is what that looks like. So here we have ThoughtBot. I'm defining ThoughtBot as an atom that holds ThoughtBot attributes. So an atom in Clojure is a reference type. Again, this is the box. So the box is named ThoughtBot. It holds an immutable map defined up here. And there's a controlled way for moving things through it. So this function here, swap bang, is how you tell Clojure, hey, I want to take the value that's in the atom and swap it for a new value. But the way you do it is you give it a function, a pure function, a side effect-free function that says, hey, I want you to run this function on the value that's in the box now. That's going to give you a new value, and then swap out the old one and put the new one in there. That's what swap is doing right here. So we start off with an employee count of 50. This is going to increase the employee count by 1. And you can see down here we're up to 51. I can do it again. We're at 52, 53, 54. But the important thing, but that's what is in the atom ThoughtBot. If I go look at the ThoughtBot attributes, it's still back at 50. The values don't change. We just put new values in the container. This is how Clojure represents change over time. Let's look at one other example. So atoms are nice because they control how you access something. So what happens is when you say swap, the atom will check the value. It'll say, what is the value now? It comes out, okay, it's 50. It says, I'm supposed to apply increment to that. It's 51. Now, is it still 50? It is? Okay. Then write atomically in one instant of time that now it's 51. And nothing can get in between there to get to an inconsistent state. It's an atomic change. It's a check and set. And so there are no race conditions. There are no mutexes. There are no locks. If you've done concurrent programming and you've played with those things, you know that they're pretty awful. Clojure we don't need those with atoms. Let's look at another example. So atoms are great when you have one independent piece of data and you want to swap stuff in and out of that box. But sometimes you have multiple pieces of data that kind of depend on each other. Classic example is a savings account or a bank account transfer. So I have a checking account over here and a savings account over here, and I want to move $10 from pesos from checking to savings, and that needs to happen in one go. Either it needs to happen completely successfully in both accounts, or none. Right? We can't transfer to 10 and then forget to decrement this one. We always want the instant in time. It's like this, and then boom, instant in time later, it's consistent now with the new set with the money transferred over. So Clojure uses a thing called refs for that. And refs use what's called software transactional memory. So I imagine we've all used a database here that has transactions. This is transactions, but brought into your code. Almost exact same idea. So in Clojure, that looks like doSync. So doSync establishes a transaction. It says, hey, I'm about to do some stuff, and I want this stuff to have these characteristics. I want it to be atomic, meaning all the change happens or none of it happens. I want it to be consistent, which means I can provide validation functions that say, make sure the count never goes negative, or make sure the transfer isn't too big. You can provide functions that say yes or no to whether or not it's going to happen, and also isolated, which means transactions can't see the effects of other transactions while they're running. So we can have multiple transactions start, and they won't hurt each other. They'll just figure out how to get in line eventually and process. So let's run this. We have our checking account, has 100 in it, savings account, same, and we want to, this is our function for moving from checking to savings, and we're going to move 10 from checking to savings. So if we do that, and then look at our balances, savings balance is 110, checking balance is 90. So this worked. Now the thing that's cool to me about this is that Clojure enforces changing things this way. If I forgot that doSync block, alter will not work. They would say, no, you can only do this inside a transaction. You can't forget. It helps you not make that error. And also, this swap bang that I showed you with atoms and this alter function that I'm showing you with refs are the only way to change what's inside these reference types. You can't just go in there and start mucking with them in an uncontrolled way. So it's very easy to see exactly where in your program you're doing things that change things over time. So what you end up doing, and what Clojure programs tend to look like, is mostly pure functions. So a pure function takes a value, does something, and returns a value. It doesn't look outside itself. It doesn't examine the state outside the function. And it doesn't have side effects on the external world. Think about writing a test for something like that. Incredibly easy, right? Value in, value out, no dependence on outside state, doesn't change the outside world at all. So Clojure programs end up being like 90% functions like that. And then a little tiny bit over here with reference types for when you actually need to model change over the world. There's a database written in Clojure called Datomic. And this is an entire database, a full production quality, split over multiple servers, complicated, real database. And Datomic has one atom. It has one reference type. And the rest of the code is all pure functions, just transforming values. I think that's kind of beautiful. So I'm finding that the code I'm writing is really nice. It's nice in Clojure, and it's also affected my Ruby in a positive way. I'm now thinking about how little can I get away with mutating? And when I mutate, can I control it in the most extreme way possible, to the biggest extent I can? And I'm really liking what it's doing for my code. So let's look at another language feature that I'm a huge fan of, macros. So let's say that I really don't like the way Clojure is a prefix notation language, meaning I don't like that it's +1,3. I want to do 3,1 plus. So imagine if in Ruby you wanted to change a.b.c to not mean call b on a and then call c on b, but to be reversed. Like I want to write a.b.c, but have it go call b on c and then a on b. That's like an equivalent change to what we're doing here. So in Clojure, you can define a thing called a macro. And a macro runs right before Clojure compiles. A macro gets a chance to change your code around before the compiler gets it, and lets it do surgery on that code to reorder things or change things, and then it gets compiled. So here, I can actually make this work using postfixed here with this 1,2 plus. This is totally not valid Clojure without a macro, but because I have that, it evaluates to 3. And the macro is actually quite simple. It takes an expression, and it constructs a list with the last thing of the expression, which is the operator, and everything except the last thing of the expression, which is the arguments. Think about What else we could use this for? How about unless? So Clojure actually does have an unless. They call it if not. But we can write unless in 2 lines. An unless takes a test of then and else, and it creates this for us. And this will work. We get our then, and we get our else. This, to me, is kind of mind-blowing because it lets you change the language in crazy ways. It lets you get in there, manipulate the language before it actually executes, using the full power of Clojure. Now, imagine we are in Ruby land, and we don't have unless. So imagine that Matt's never wrote unless. I'm like, oh, it'd be really nice if I could just have a keyword unless that would let me do if not, whatever. Can you write that in Ruby? Can't write it in Ruby. Because there are certain things in Ruby that are keywords, that are language features. And there's a wall between you and certain parts of Ruby, right? You can't write if yourself in Ruby. You can't write unless yourself in Ruby. You have to write it in C. You have to write it in the language level. So there's this big wall, and there's actually a bunch of stuff behind that wall that is Ruby, and then there's some stuff that you can do on your end to change the language. Ruby's actually fairly flexible, but there's still a bunch of stuff behind the wall. In Clojure and in Lisps in general, the wall is way further back. There's a few things behind that wall, but then the rest over here is just macros. You tend to build Lisps and Clojure in particular out of themselves. And you push that wall of stuff you can't touch way back. Because you can just, rather than special forms built into the language, you can do stuff with macros that lets you change the code around before it compiles. Really powerful feature that I really am a big fan of.
He asked for questions during the talk. Do you know if you would be able to do unless in Rubinius, probably, which I understand the wall is way beyond.
Could you do unless in Rubinius? I'm not sure. I'm not familiar enough with Rubinius to answer that, unfortunately. You could probably implement it in Ruby to run in Rubinius, right? Because Rubinius is written in Ruby. But I still think you couldn't define it in like normal Ruby code inside Rubinius. You'd have to define it inside the parser, inside the language itself, into the interpreter. Other questions? Yeah.
Yeah, you mentioned before that now, after learning Clojure, you tend not to remove stuff from the database. So for example, you were explaining what you will do with that subscription. Instead of deleting the record, you will just like put an end date.
Yep.
You said that you think that has made your applications or your code better. Can you explain why do you think that?
So if I said it made my code better, that might have been I might have misspoken slightly. What I meant to say is it makes it easier for me to understand my data. So what we were finding is people, if I blew away that old record, I've lost data now. So I couldn't tell that someone signed up, canceled, and came back and signed up again. And so by just recording these events and treating these events as immutable things and recording new ones, I can see the history there. And I don't lose the fact that someone used to be a subscriber. That's the question. Okay, one more thing I want to show you, and then we'll wrap up. So we've gone through reference type, we've gone through macros. Let's look at Clojure script. So I have some amazing news. I have some great news. All this stuff, this is a JVM language, Clojure, JVM language. It compiles into JVM bytecode, runs in the JVM. We can take that identical code, all this great stuff I've just showed you, literally all these things, and we can use them and compile them down into JavaScript and run in the browser. Which means we don't have to write JavaScript. Right? Yeah. So that's kind of exciting. I think you really should be excited about this. Like, you can use a great language with really smart semantics and good ideas and macros and reference types and immutable data structures and all that, and you can use it in the browser. It compiles down to JavaScript code that then gets optimized by Google's Clojure compiler. It turns into really fast, really tight code, dead code elimination. It's beautiful. And also, you can get some really cool things. One is source maps, really good source maps. So the classic thing of when you compile to another language, it's like, oh, but then how will I know what's wrong in the original code when I have a bug? Clojure script outputs really good source maps. So you click it, if an exception shows up, you can click it in the browser, in the Chrome console, in the DevTools. It will load up your Clojure script file and show you it's on this line. And like you have Lisp in your DevTools in Chrome. So that's one great thing. The source maps are excellent. And the other great thing is a browser-connected REPL. So you notice how I've been evaluating code on the fly in my editor? The way Clojure does that is it spins up a server running your code and lets you send code to be evaluated in there. So I'm sending code to it, it evaluates, and then it sends it back to me. So right now my editor is connected to a running server on my computer. But that server can also be in the browser. You can tell browser, hey browser, I want you to spin up a REPL in there, like a console. And then from my editor, I can send commands to my browser and get data back and forth. I don't need to reload even. Pretty powerful stuff, really cool. I'm going to show you a really quick example of some Clojure that I wrote with Chris Hunt, who you saw yesterday. This is, this is a maze generator and solver that we wrote in Clojure script. So each of these mazes this is JavaScript running on a page. The green and red are a little hard to see, but first we generate a maze randomly, and then we try to solve it. The green is the path that we're exploring. Red means we got to the end. It was not good. We have to back up. This is just a depth first search. Trying to solve this maze until we're going from the top left to the bottom right. Bottom right is solved. You can see it's pretty dumb. Should have taken a right, took a left. And I'll show you what it looks like briefly. It's over here. So this is the core functions. So I said that in Clojure, my programs tend to be mostly pure manipulation, and then a little bit over here where you deal with the mutable world. So in Clojure, most of our things, this is the code for the maze generation and solving, and all this stuff takes values and returns values. There's no mutation going on in any of this. So all these things you see here are simply taking values, returning values. That's our core. And then outside our core, we have to somehow deal with the DOM eventually, right? We need to deal with a canvas. So we isolated that into a file called draw. And here is where we actually deal with native JS objects. And so here we say we get the canvas. We can actually call. Here's interop, us interacting with JavaScript. This is JS/documents get element by ID, get context. And now we can see us doing set bang. We're doing mutable stuff here. This is like, okay, icky stuff is happening here. Call it set bang. Be aware that you're mutating things. There's also some nice things like do to. So this is, do to says, it takes an argument context, and then calls begin path on it, and then calls .move to with these arguments on it, and then calls .line to. Just a nice, convenient shorthand for expressing things when you do the same thing to an object over and over again. But the story of this is great. Source maps are great. Browser connector REPL is great. It's fast. The optimizing compiler is really good. And most importantly, we don't have to write JavaScript. So awesome. If you've been intrigued by this, I hope some of this stuff has at least stimulated you a little bit. And okay, maybe I need to at least check into this thing, learn a little bit about it. I wrote a blog post that I think will be useful for you called Tips for Clojure Beginners. It's on the ThoughtBot blog. If you Google that phrase, it's the first thing that comes up. Also, I have my talk notes on my GitHub account if you want to link to it there. I'm R00K on GitHub. And this is a great way to get started. Thank you very much.